So this is an old-fashioned thermos. It's shown in the image here. It has an internal chamber which consists of a cylinder on top of a hemisphere. Now that's kind of hard to see. It's right in here, so I'll redraw it for you. It looks like this. There is the cylinder, and then at the bottom there's a hemisphere, which means half of a sphere. And that's the radius of the hemisphere, and which is the same as the radius of the cylinder, and the cylinder is 10 centimeters in height. Now, to give you a better idea, I have here a cylinder, and I have half a sphere. It's kind of hard to see, but you can imagine that if you put them together, you get the cylinder or the cylinder with the hemisphere. So it looks kind of like that. Okay. All right. So our job as engineer is to design this thermos, which means selecting the radius, such that it will contain a volume of 500 centimeters cubed. Is that half a liter? Yeah, half a liter? Yep. Okay. Well, here's what we know. We know that we have this cylinder that has some volume, and we're going to add half the volume of a sphere, and that needs to equal 500 centimeters cubed. And you will recall from geometry, and of course they're right here, that the volume of a cylinder is pi r squared times the height, which in this case is 10, plus a half times the volume of a sphere, which is 4/3 pi r cubed, equals 500. And so this is the equation that we want to solve. And we really don't even need to simplify anything, because we can enter this into our calculator, this side in y1 and that side in y2, and we'll just have to get a graph. So let's see here. Going into y equals, y1 is pi symbol x squared times 10. I'm using x instead of r. Then plus parentheses 1/2 times parentheses 4/3 times pi symbol times x to the third. And in y2 we put 500. Now the hardest part about this is going to be setting the window so that we can see this graph. So the x-axis will be the radius, and the y-axis is the volume. And we know that we're going to have a horizontal line at 500. So we're going to need to set our y-min and our y-max something on either side of 500. How about 450 and 550 for the y-min and the y-max? And then realistically, we can't have a negative radius, so our x-axis could start at 0, and I don't know, let's just try 10 to start and see what we get. And there it is. So we just have to find that intersection to solve for the radius that we need. Second, trace, intersect. First curve, enter. Second curve, enter. And then guess. You can just move the cursor near the intersection and press enter. And it looks like we need to select a radius that is approximately 3.6 centimeters. All right, let's talk about the problem of this big old storage box here. The volume in cubic inches of the decorative box shown in the figure can be expressed as the product of the length of its sides as the volume equals x cubed plus x squared minus 6x. Write linear binomial expressions with integer coefficients for the box lengths and height. So we'll need an expression here for this length and an expression here for the height. And then find the dimensions of the box if the total volume is 2,500. Well, there's really two parts to this question. The first part is that we know the volume, which is x cubed plus x squared minus 6x, that volume has to equal 2,500 inches cubed. So I think the first thing we should do is solve this to find for the value of x. And then we could plug it in here and we'd have the width, and then we'd just have to figure out the other two. So this we can solve by graphing. We can set this side equal to y1 and this side equal to y2 and find the intersection. So we'll go to y equals, clear out our old equations and put in the new. Now, the hardest part, I think, will be setting the window so that we can see the intersection. y2 at 2,500 is going to be a horizontal line. And so in our window, we're going to want to set the y min and the y max on either side of 2,500. So we could do y min, say 2,000, and y max 3,000. And that will capture this horizontal line. And then I don't believe it makes sense for any of these dimensions to be less than 0. But so let's set x min 0 and let's try x max 10. And we'll see what happens. And we didn't get it. Well, we're obviously not in the right range. So 0 to 10 didn't capture it. Less than 0 doesn't make sense. So we must have to go bigger than 10. So I heard someone say 20. Let's go 0 to 20 and see if we capture it. Oh, there it is. So we just need to find this intersection point to get the x value. So second trace, intersect, enter to guess. And it looks like, let's say, approximately 13.4 inches. Excellent. Alright, so now we could plug 13.4 into x minus 2 and get the width. But we have to figure out how to get these other units. And so what I would propose is, because we want linear binomial expressions with inner coefficients, I think we should do synthetic division. Or we should factor this thing. Well, tell you what, let's try factoring. Let's see if we can do it factor. Because when I look at this, I see that there's an x in every term. So I know that we could factor an x out of every term, and we would end up with x squared plus x minus 6. And then this quadratic trinomial should be able to be factored into two linear binomials, and one of them should be this width, x minus 2. So what would the other one have to be? X plus 3. Okay. So now we know that on this box, one of the dimensions, say, is x, and then the other one is x plus 3, and so we just need to figure them out. So the width would be x minus 2, so 13.4 minus 2 is 11.4 inches. And the height is x, so that would be 13.4 inches. We could just say 13.4. And then the length is the x, 13.4 plus 3, so that would be 16.4 inches. And we could check our answer by just multiplying those. I'm going to go ahead and do that. 11.4 times 13.4 times 16.4 gives 2505. Do you know why it's not exactly? Because we rounded right there. That 13.4, we rounded that. All right, we did it.